Welcome, guys. I'm David Montero. You guys are BocaJS. My God, this is loud. All right. I played with it so it wouldn't be so loud. Thank you guys for coming. As always, we're going to have a great presentation. We'll talk about it. Geovanny will have a chance to present in just a second. Wanted to let you guys know a couple of things. Thank you guys for coming on a Monday. Every single time you guys hear me talk here at BocaJS, I tell you every first Tuesday of the month. Well, for personal reasons, I've had to sort of change it, so thank you guys for coming. If you're interested in coming next month, it'll be on Wednesday. Simply a conflict of scheduling that we had in the situation. Nothing to do with Sendine Spaces, which is one of the sponsors here, which sponsors the location. We'll talk about our other sponsor in just a second, but you know, thank you. So, guys, this is, thank you, Sendine Spaces, for the location. They're a fantastic co-working space if you want. Usually there is a place you can put your business card. If not, come in, see Amanda, tell her you saw her in any one of the meetups, especially the BocaJS, and they'll give you a week free to try out to see what it's like working, not from home, not from your office, from somewhere where it's more cozy and private, and you know, you don't have to worry about your laptop when you're, you know, want to go to the bathroom for Starbucks and all that. So think about it. So. Gravity IT has been with us for, it's been, I believe, over a year that they've been sponsoring us, and thank you very much, and so I'd like to say something about it, guys.
Hey guys, thank you for the warm welcome. Thank you guys for having us. So we do sponsor some of these events. My name is Felipe. My coworker and colleague is Madison Davis. We're with Gravity IT Resources. We're an IT staffing firm, and I know you guys have heard it all before, but I have a couple questions for you. So, who has bills they have to pay? Assuming you guys all do? All right. Now, who would like someone else to pay their bills for them? Assuming all of us, right? What if I could tell you I could be that guy? Probably wouldn't believe me, but we've paid over $200,000 in referral fees this year alone. Okay? So we have a referral fee that is unmatched. We do it both for permanent and contract roles. So that's what kind of sets us apart. The rest, we're a referral-driven company that focuses on talent, and if you're a smart person, you're probably surrounding yourself with smart people. So we want to get to know you, we want to get to help you out. We would also like to help out your friends and family. So we'll be sitting right over there in that corner. You guys can come and meet Madison and myself, and we'll be glad to tell you more about our company and how we can help you guys out moving forward. Thank you for having us. Hey. Thank you very much. Thank you for having us.
Thank you. Robert's talking about the hackathon we had at JM Family. Very nice. We're also sponsored by JetBrains. If you guys stick around till the very end, there'll be a website you can go to with your phone, and if you get an automatic ticket, and then you guys can see if you win. License for 1 year for JetBrains. Okay. Meetup is having problems, so everybody knows that. I don't know if you're aware of it, or organizers have it, so just definitely meet us. Continue going to meetup.com/BocaJS, which is probably how you found out about it. If you ever see something where all of a sudden something happens to Meetup that's unusual, we do have a website, BocaJS.org. It always points to the Meetup page. It doesn't do much. If anything ever happens, just remember that page. If you're interested in these kind of talks, but more personal, I do one every week on my YouTube channel, which is BocaJS. I'm sorry, YouTube.com/BocaJS. We have unusual things. I made sure to do something really, really stupid, but very, very interesting and relevant to JavaScript. All right. If you guys want to go to pi.bocajs.org. You can download TensorFlow kit right now for 50% off. But you're not here for me to talk and advertise about my product, are you? By the way, Gravity's sitting over there. If you want to talk to them, or if you want to get paid, talk to them over there. And we're here to see Geovanny. Geovanny.
So my name is Geovanny Fajardo, and I'm with a company called Smart Procure here in Deerfield Beach. And I want to introduce you to neural networks with JavaScript. Part of this is a dual presentation, is because there is a relationship between the functional programming aspects of programming and neural networks themselves. So my hope is that you will be able to see that connection, and that may help you to get a better understanding of what how neural networks work. So this is an interactive presentation, so if you have your laptop and you want to bring it out, we can do that. And at the bottom of this slide, you can see the URL, and you can go there and get the slides. So is
Sure. I'll put it on the Meetup page.
okay, cool. So if you want to get the slides now, you can do it. If you want to wait until later, that's fine. But in that way, you can follow me as I'm guiding you through the slides and speaking about the different subjects that we're going to talk about today. Also, for this particular presentation, there is a GitHub repository that I put together for you. And at the end of the presentation, you will be able to go there and also get all the code and any additional code that I might be putting there, providing a service for you guys to be able to give me feedback or contribute to it, or just use it as you can as you see fit. So, so the good news is that everything that you do in the everyday life and just at work is got a relationship to this idea of functional programming and neural networks, because that's where it was born in the head of somebody like you, right, and I. So a lot of the things that you think of, if you think about it in your everyday, will relate to this subject. So the key here is that everything is information, and information is everything. So everything that you do with programming has to do with information, even functions. Functions are just a way to encapsulate information, encapsulate knowledge. So that's the main idea behind all this. And as I go through, you'll see what I'm trying to tell you regarding that. So let's get started. Wrong way. There we go. So the first thing that we're going to look at is the idea of functions, right? So functions are just like a black box. You put in something in and something comes out. You have an input, you have an output, and you have some kind of a knowledge that is encoded in that function, right? So, but in this talk, we're going to talk about a specific kind of function, what is called a pure function. So it's a pure mathematical concept of what a function is. It's a function that has no side effects. In other words, whatever you put in today is going to come out tomorrow, is going to be the same value. There will be no difference. It's also known as a stateless function because there is no state. If you're familiar with something like React, you have heard of stateless components, right? So those are pure functions, pure functional components. So that's the idea of a pure function. It's a pure mathematical concept. As you can see, f of x equals 2 times x has no state. It will be the same. If you give it an x today, it will be the same a million years from now. So that's a pure function. So the next thing that we're going to touch on is objects. We're all familiar with objects. And objects are just a way to encapsulate information, right? If you come from an object-oriented programming world, you would think of a class as a blueprint and an object as the instantiation of that class, right? But if you look at JavaScript and many other languages that are no object-oriented programming, you'll see that there is these things called data structures, right? In JavaScript, we can create an object, as you see right here, a box, and it's not an instance of a class. It's just a data structure that we're creating, and you can see it's got a method associated with it. So that's an object. So we talked about pure functions and objects, right? So the next thing we need to think about is input and output, right? Is everybody familiar with the modern JavaScript ES6 syntax? Yeah, okay. Well, I use it a lot through the slides. So if you're not familiar with it, I'll try to explain it just a little bit. So as you can see right here, we have information, we have inputs, we have outputs into this function. The input happens to be right here an input that has two vectors. Vectors are just array. One is 1, 2, and the other one is 3, 4. And we're going to put that, and we're going to define a function called f. And as you can see right there, we have deconstructed the two vectors, and we're just going to multiply those two vectors together, and that's our function f, right? So we have inputs, we have outputs. The output is going to be the product of those two vectors. And at the bottom, you can see right there, we have the length is 2, the output from the first array is 3, and the element in the array is 3, and the other one is 8, and you got a function that is multiplying vectors, right? Vectors and matrices and those things are really important when it comes to neural networks, because if you try to work with just pure numbers and loops and things like that, whatever computation you're trying to do becomes very too much for the system to handle. So there are optimizations that you can do by using vectors and matrices and concepts from linear algebra. So that's just an example of what kind of functions we're talking about. And these are, in this case, these are pure functions, okay? And they're operating in these objects that we just talked about. So the next important concept in this whole thing is the idea of function composition. I tried to put together an image that will give you an idea of what function composition is. So as you can see, on the first box, we call it G. The second one we call F. And we have in the first one as an input a sphere. And then through some process, we don't know what it is, a cube comes out. And then we have another box, another function, F. And we're going to put the cube inside that box. And then we have another geometric shape coming out, right? So that is function composition, basically. You have input, and you have output, and the output of the first function becomes the input of the second function. Make sense? So when you have functions like this, you call them higher order functions. Just a function that takes in a function and or outputs another function, right? So those are higher order functions. So far we have functions, we have objects, and we have the idea of function composition. All right? So an example, if you're using modern JavaScript, you might be familiar with the functions map and reduce, right? Map is a function that will map a function to an item in an array. In this case, we have 1, 2, 3, 4, and we're going to map the function 2 times whatever the value in the items, right? So that will give you, that's a higher order function because it takes a function and it maps it to a element in an array. Then the other type of function you have is reduce, right? Reduce is another function that is common now in JavaScript. We have arrays, and we can reduce those arrays using the reduce function. Basically, it allows you to have an accumulator and a function that is mapped to every element in the array, and then you're able to accumulate those values inside it. So in this case, we have sum is the accumulator, value is the value that is in the array, index, we're not using it in this case, but it gives you the index of the element you're working with. And then we have a simple operation, just summing all the values together, and that's going to be the added values. Make sense? So there is 2 basic examples of functions that are higher order functions that are available to you in JavaScript to use. Now, the next concept is understanding function composition. As you can see in the top right, we have the function f and the function g, and then we have another function called h. And basically what is happening is that, just like the picture is showing you, f is receiving the input from g, and it has an input called x, right? So x is a value. It could be any number. And G and F are functions. And that's how they come together in function composition. Now, imagine if you're trying to compose 10 functions. Imagine that you need to bring together more complex logic. So writing in that fashion doesn't make any sense, right? It's going to be a lot of parentheses, and it's not manageable. So in order to achieve a more manageable way to compose functions, we can define a higher level function called compose, right? So compose, if you're familiar with the spread operator in JavaScript, we have a function that takes X number of functions, then we convert that into an array, and then we have an argument that goes in it, and then we reduce that array of functions with the argument, and then we grab that argument and pass it to each one of the functions in the array of functions. Basically doing the same thing, but now with an array of functions. So you can have as many functions as you want, right? So you will just call that function and say compose F and G, and then you will get a composition of your function. But it's really hard to read function composition, because if you look at that H function, you have to read it from right to left, right? So if you're used to reading Hebrew, then everything is okay, but if you're not, it's kind of crazy, right? So in order to mitigate that problem that we have, we're going to define another function. We're going to call it flow, okay? So flow, what it's going to do is just going to be like compose, but if you notice, where we have functions right there, we're going to reverse that array, and then we're going to do the same reduction that we did before. In essence now, instead of your composition reading from right to left, you're going to be reading from left to right, right? So it gives you something more readable for you. So now if I want to use it, then I can just say let H equals flow FG, meaning I'm going to have some function that is going to be composed of F and G, and is going to, I'm going to be able to use it to do whatever I want, right? So that is more readable than saying F of G of X, especially if you have multiple functions. Everybody sees that? Make sense? I think the first time that you see flow is kind of like confusing, because it's using that modern syntax, and you have multiple functions that you have to go in it. But in order to make it easier for you, if you download the slides, I actually wrote the code. I don't know if you guys are familiar with RunKit. So I wrote the code for you, and if you go through the slides, you can always click on that picture and actually go and execute that code. So it's right there for you. So download the slides if you want to get a...
It's in the meeting on the comments.
Okay. So we're good, right? We got functions, we have function composition, we have objects, and now we have another tool, flow, right? Okay. Okay, the last tool. So you're almost done with functional programming, because at that point, that's really all you need. So you're learning functional programming right now. So the next thing we're going to do is we're going to introduce the concept of currying, okay? So currying is just really the first function execution, okay? So you have a function, it takes 2 arguments, and that's fine. I mean, that works. You have the normal add right there. But another way you can think about it is that you can say, I have a function called add, and it's going to take argument A, and it's going to give me a function back, and then it's going to take argument B, and it's going to give me the result. Okay? So you can see the modern JavaScript construct for that on the top right. And there is a visualization that you can look at too. You can see we have a function that takes 4 arguments. It gives us a function that has 3 arguments and is waiting for the next one. And once it gets all the arguments it needs, it goes ahead and executes. Okay? So the first function execution. That's all what the currying is. Okay? How would you use this? If you think about it, flow allows you to compose things together or bring functions together, right? Well, currying allows you to separate, break them down, okay? So the idea of being able to put things together and be able to break them down is important because it will allow you to be able to compose your logic better. The whole idea of functional programming is using functions to put together all the logic that you need. There is no such thing as a class or an interface or anything like that. It's just pure functions that allow you to compose and create new things, right? Create your logic using functions. So, as you can see right here, let's go through the example. You have add2, and it's simply defined as add with the parameter 2 given, right? So what do you think that function is going to do? Right, it's going to give you a function that if you pass it an argument, it's going to add 2 to whatever argument you gave it, right? Now we have the result right there, so result equals add 2, you give it 2, it's going to give you 4, right? And just like before, there is the result of what we did, right? So we have normal add, we have add, we created add2, we say add2, the result is 4. So now we have functions, what we call pure functions, we have objects, we have function composition, and we have currying, okay? So we have a way to be able to bring things together, we have a way to be able to split them apart, and now we're going to do something that is called point-free style programming, okay? When you think about point-free style programming, you need to think about how declarative the code is when you write in this style of programming. For example, let's look at the other function that I have there, add2 then 3, right? So now we apply our new function that we created, flow, and we can say flow is a function that will take add2 and add3 and do exactly what it says, right? I think even a first grader can tell you if they just read it, because they can read it and say add2 and then add3, and that's what the function does, right? So the code becomes very easy to read, and it's easy to compose things, it's easier to put logic together, and more importantly, it's easy to maintain, right? So maintainability of the code and readability of the code and all that becomes easier when you start thinking about functional programming and point-free style, right? So at this point, that's what functional programming is. It's just you use flow, you use curry, you get your functions, and you're doing functional programming with JavaScript. All right? When you see it for the first time, it's a little bit crazy, but I hope, like I said before, if you download the slides and you start playing with it, you'll see what I'm talking about. So why did I take you through this whole thing, right? I took you through all these things that we went over for you to see something that is really, really important. It's the basics of any computation. It's the basic of systems programming. It's the basic of how logic gates and how computers work internally in terms of hardware and all that. Is the whole thing that we're doing at that low level and even at this high level is that we're creating these things called computational graphs. These are directed graphs, right? Why did I take you to the simple concept of an object and a function? The simple reason is that when you have a computational graph, you can have input that is information and object type, right? And you have functions that are knowledge encoded, right? So right here we have that function, that object graph that says that you have an input, which is data in object form, and you have two functions, add2 and add3, and you have an output, which is again data, right? It's information in object form or number form or vectors, or whatever you want, right? So, and the important thing to understand here is that the way that these computational graphs are joined together is through this basic idea of function composition. Make sense? So the next thing is trying to understand how we're going to solve this problem, right? So neural networks, when you hear about it, everybody's talking, oh man, these things can do anything, right? And why is that people think of neural networks in this way? How did we arrive to that? The way that we arrived to neural networks and the understanding of what they are and how they work is that we started thinking about how to solve problems, right? And we have a great example in nature of how to solve problems, right? We have a big problem that we want to solve. We chop it down into smaller problems. We try to make sure that those problems are similar, right? And then we try to solve the small problems first. And then you put all your little solutions to your big problem, and all of a sudden you have the big problem solved, right? So breaking down the problem is essential. Why is it important for us to understand that, and what do you gain by doing that? So what you gain is that if you break things into small steps, you have less risk, and you have to be careful though, because you have to have a sense of how small your steps have to be. But this whole idea is called divide and conquer, and is crucial to the idea of neural networks, right? The other idea is that there are different kinds of problems. There are problems with one or more solutions, and there are problems with no solutions. That is very important, because what that's telling you is that that if you have a problem and you cannot solve it, you cannot let the machine run forever trying to solve the problem, right? If the problem has no solution, you have to establish some kind of a limit. You have money. You have everybody that is using cloud computing knows that if you go to Amazon and just run a machine for 15 days, you're going to have to pay the bill, right? So you have to be careful on how you utilize the resources available to you. So understanding which problems are the nature of the problem is important. So another important concept is the idea of a context, right? So every problem is in a context, right? Right now, we know so many things about science, and 100 years ago, we didn't, right? The context has changed over time. The more information you have, there is more richness of knowledge. There is more stuff that we can grab and think about, and more information that we have gathered, and therefore apply that information within the context of the problems we're trying to solve, right? For example, in quantum computing, why is so important? Well, if you think about the pharmaceutical industry, they're working on trying to figure out the pathways for chemical reactions, right? The problem with that is that you cannot even simulate a simple chemical reaction right now of more than 3 or 4 molecules, right? But with quantum computing, and when we have that information, when we have that knowledge available to us, then we'll be able to solve these harder problems. And that has been happening over time, right? So this idea of the context that you're in is what gives you the ability to be able to solve problems. So whenever you think about a neural network, think about you're creating your own universe of solutions. It's going to be, you're going to be in charge of providing that information. You need to understand your domain. You need to understand what is going on in terms of data yourself first, so you can put together the question that you're going to ask. So half of the struggle with neural networks, or more than half of the struggle, is trying to figure out what is the right question to ask, understanding your data. So for that reason, that richness that context is going to be provided for you, by you, to the network. Okay. So how did scientists, computer scientists, come up with this idea of neural networks? Well, they use the brain, right? We have neurons, and they come up with this idea of a simple function. So when you think about neural networks, and you see that picture that always is shown, where you see the nodes right there, and the layers, what you think about is that now that you're in this talk, what you need to think about is that the input is just some kind of data, some object. And the hidden layers in the network are just functions. Functions like that function right there. So in this little amount of code, I have encoded the function for a neural network, right? And you can see right here where I'm using flow, I'm using reduce again, and the only thing that I have introduced that is new in this whole thing is the idea of nonlinearity, okay? And the nonlinearity is a way to give richness, more context to your solution. It's a way to make the solution space, the solution of possibilities, bigger, all right? A nonlinearity, and the reason why neural networks are many times used as classifiers. Classifiers mean you give it an image, and it will be able to classify it based on a label, right? You give it a dog, it has been trained looking at dogs, and is now when you give it a new picture of a dog, it's going to give it to you. And the way that that's achieved is by understanding this idea of nonlinearities and function classifiers. One of the most important classifiers that we use everywhere, even in electronics and other things, is the idea of the sigmoid. Okay, the sigmoid is just a function that when you give it some number, is going to give you either a 0 or a 1 in a very smooth way. Okay. For neural networks, you can assign a nonlinearity, and when you work with a neural network library, you'll see that you'll have a bunch of choices of which one to choose. So each problem is special in a way when you assign these parameters. Okay. So now we're just going to really quick go through how do we put together the neural network. Okay. So a neural network is got layers. It's got input layers. It has an input layer. It has an output layer, and it can have multiple hidden layers depending on what you're trying to do. So an input layer is data. All the hidden layers are nodes that encode functions. Okay? And the important thing to understand is that the functions are functions with weights associated with them. All that is if you remember a linear equation, right? A line equation from high school, is got a weight associated with it, and it's got a value associated with it, and it's got some kind of intercept, like a b-intercept, right? So is the simple form of m times a plus b, right? That is a linear function. Now, the neural network is a function, is a function with multiple weights. So you have m of 1 times a of 1 plus a of m of 2 plus a of 2, etc., depending of how many neurons, how many layers you want to have, okay, or what your input, nature of your input is. All these things are what is called a hyperparameter. So in here, we have a neural network with one input, okay, so the function that is going to be inside that, the weights associated with that is 1, and then the hidden weights, because the input has one parameter, are going to also have functions that are going to have one parameter, one weight, right? And then what you do is that once you have that linear function with multiple parameters, multiple weights, you apply the sigmoid. And what the sigmoid does is that it brings down things into something that is more manageable. Instead of looking at infinite possibilities of numbers, now you're looking at a range between 0 and 1. So even though there is infinite number of numbers of digits of numbers that you can have between 0 and 1, you have a boundary to work in. So it just brings down infinity into that range. So the important thing here to understand is that you're always working with numbers between 0 and 1. And that has a huge implication. I'm going to skip this for right now. So why does it have a big implication? Because none of our data is zeros and one, between 0 and 1 all the time, right? It's really rare to encounter that. So what you need to do when you prepare your training data, okay, your training data sets, is that you need to feed information in that range, right? So you need to do something that is called normalization. So you need to bring all your data within that range so that the values are always between 0 and 1. You need to make sure if you're doing a classification problem, you need to make sure that you label your data, right? So if you're classifying images, you're going to have somebody go, some human, go and look at each of the images and be able to say, this is a dog, this is a cat, this is a deer, right? And label those images. So it's a very tedious process to do that. So normalization is bringing down the data into that range of zeros and 1. And then once you get an answer, you have to do the inverse, right? You have to bring it back to your, denormalize it and bring it back to the range that you're working with, okay? So that is really important when it comes to preparing your data. Now, this is a very, I'm not going to go through all this, but you can read it later. The whole idea here is that you have this graph, right? This directed graph, and what you're trying to do is to figure out of all those weights and all those biases, how do you change them so that this huge function will give you the output that you want? That's the whole idea of training. Optimizing the values, the weights, inside your neural network. Remember, it's a bunch of little functions, and you're trying to optimize those weights so that the value that comes out, the output, is what you desire. Simply, putting it simply, is you put a picture of a dog, you want the neural network to be able to process the data and give you back that the picture was a dog that matches the labels that you have. How do you achieve that? Okay? This goes into a branch of mathematics that involves something called tensors. That's why the Google framework to do neural networks is called TensorFlow. Okay? And basically what you're doing now is that you're trying to figure out in these hills and valleys where the optimal values are. So you can see this, it looks like a bunch of mountains. You're trying to figure out the minimum values that will yield the solution that you're looking for. And the way that you do that is that you have to figure out a way to gauge what the difference is between the answer that you have right now at a given point and the answer that you want, right? So that is called an error function. So what you see on the left, on the top, E equals 1 over n from I equals 1 to n of O prime I minus O I square is the error function. What that simply says is like, here is a way for you to figure out how right or how wrong you are, right? So then what you want to do in a neural network is to figure out what the error is so you can go and fix the weights and adjust them so that the values that you want the values that you're getting in the neural network get closer and closer to what you want. Okay? That whole process is called backpropagation. And it's not an easy algorithm. TensorFlow gives you the algorithm already figured out, so all you have to input is the numbers. But what is important about this is the idea of hyperparameters. And this is what I wanted to get to. Several hyperparameters that you need to be mindful of. One is your error threshold. Another one is your learning rate, your momentum, and the maximum number of iterations that you want to go through, right? So the maximum number of iterations determines if you're going to go into an infinite loop or not. That's why I was telling you about there are problems that have no solutions and problems that have solutions, and then you have to be able to figure out how close you really want to get. And the error threshold and the maximum number of iterations allows you to adjust that in your neural network configuration. The learning rate allows you to decide how big of a step do you want to take towards your solution. Okay? And you have to be careful with that because you don't want to underperform and you don't want to overperform, right? So these are like hyperparameters that allow you to adjust the algorithm to be just right in the range that you want it to be. Momentum is kind of like looking back and saying, when I was far from the solution, I like taking big steps. But now that that the network is sensing that you're closer to the solution, I want to make my steps smaller, right? So that's kind of like what momentum gives you. And then the other thing is that laptops are okay, or computers that we have in our houses are okay for everyday tasks, but tensors and matrices and these objects, these mathematical objects, working with them is very intensive, right? So that's why you want to use GPUs or TPUs, where TPUs are tensor processing units. If you go to Amazon Web Services or you go to Google Kubernetes, you will be able to sign up for free to get access to these tensor processing units and GPUs to play with your neural network. So all that is there. Now the equation at the bottom is just how do you adjust the weight, right? So the delta of the weight is equal to the learning rate times the gradient of the arrow plus m, the momentum, minus the gradient of the arrow times the previous weight, right? So if you want to know how those hyperparameters play a role when you're playing with neural networks, that is the equation you want to look at. Make sense? There we go. Okay, so what frameworks are available there? You can code your own neural network if you want, but I won't recommend it. It's not easy. So if you want to play, you want to have fun, and you want to be able to apply it in your everyday work, then what you can do is you can either use TensorFlow.js, which is the most popular neural network framework. It's written in C, but it's got bindings to Python, it has bindings to JavaScript, it has bindings to C#, it has all kinds of bindings to other programming language. Now, I'm kind of biased because the guy who wrote BrainJS is my friend. So my network that I prefer to teach people about neural networks is BrainJS. It's that simple. It's very easy to go from getting a data set, defining what your network looks like, feeding it the data, and getting an output. So if you want to explore, you can explore with BrainJS, get your headings, understand a little bit more how it works. There is a lot of online courses that the BrainJS community has put together to help people to understand, and you can get going with neural networks pretty fast. So at this time, I have another URL that you can go to, and we're going to start going to 3 examples for you to see what neural networks are good for. So there are 3 areas that we're going to explore. We're going to explore an area that has to do with regression or curve fitting. which allows you to do predictions. Who was I talking about? Tiles? Who's sales tile? Yeah, he was telling me about he had some sales data from historic data. You could take all that historic data from your sales and analyze it and create a neural network and say, here it is. I want to be able to predict what my sales could be next year, right? So we're going to go through an example. In this case, it's in the financial market. So we're going to look at that. We're going to go, and that is for prediction. For regression, we're going to look at another example of how to do that, trying to find trends, right, in data. That's a good thing. And the last one that we're going to do is classifiers, okay? I'm going to do a very simple example of classifying numbers. So if you want to take a picture of the URL, it's right there. That's not for the slides. That's for the actual examples in the repository in GitHub. So.
Right now the link says it doesn't work.
Oh, it does?
No, that's good. It's good. But it will work on your example, and you can fix it later, right?
Right.
Guys, it's also in the comments in the Meetup. Can you take a picture? It's also in the comments in the Meetup.
So right now we're going to go to that GitHub repository, and we're going to go. I set up everything for you to be able to run it. So I'm gonna run it. But when you have the time, if you want to explore, you can go and run them. We're going to go over the horsepower versus miles per gallon example. Is an example that will show you how you work with linear regression, right? Trying to do curve fitting.
Is the links to the example in the one that you sent? I'll put the whole GitHub in the comments.
Okay. How are we doing on time, guys? Are we good? Okay.
Because they're in machine learning, stick around.
All right. Is that good? Okay, so the first thing we're going to do is we're going to import brain.js. Then I wrote a set of core helper methods, okay? One called train, another one called training errors, and the other one called get error plot, okay? So we're going to run this example, and we are going to train it, and we're going to run it, all right? Training means you're feeding your data set to the framework, to the neural network, and you're adjusting those weights. Remember, we have all these little functions, they have all these little weights, and now we're going to let the framework adjust the weights. That is training. Running means that you're going to get the output of your neural network, which is simply a object, okay, that has all the weights and all the biases information in it, all right? So that's what the train function is going to help you do. I'm a functional programming person in JavaScript, so of course I got to use Lodash and the functional programming Lodash version. And to plot, I'm going to use something called noplotlive. So from the utilities, we're going to get something called a preprocessor, which is a function that will give you the ability to pre-process your data, to do all your normalization, to do all your adjusting, and your data is not going to be clean. You're going to have to select which data you want in your data set, right? So you're going to have to clean it up. You're going to have to normalize the data. In this case, I'm going to normalize the horsepower, and I'm going to have another function that is going to denormalize the miles per gallon. And part of the normalization process is getting the streams of your data. And you'll see that if you go and dive into my normalization function. And the next thing that I'm going to get is the route data. Okay? So let's take a look at the data first. So in that example set, you'll see that there is a training data folder. And the data that I have for horsepower versus miles per gallon is just some that's weird. Give me 1 second. Okay, so we're going to get our raw data. Okay, wait a minute, 1 second. Here we go. Okay, we're going to first define our neural network, right? So brain has several types of neural networks that you can get, and one of them is called just neural network, which is the simplest neural network that you can define. Then we're going to put some options in there. Remember we were talking about the hidden layers, right? So the way that brain handles hidden layers is that you give it an array, and in that array you tell it how many neurons you want in your layer. So in this case I just want 2 neurons, okay? And then each one of the items in the array right here represents a layer. So I'm just having 1 layer with 2 neurons, all right? The next thing we're going to do is that we're going to define what the activation function, what's the non-linearity that we want. In this case, I'm just going to select sigmoid. Okay? The next thing is the training options. So this is where your hyperparameters come into play, right? After I was playing with it and felt comfortable with it, I found out that the best error threshold that I could give for this neural network in particular, for this problem, was that number, 0.0138. And I also found out that the number of iterations that it took to do a good regression plot for curve fitting was going to be 50. But I commented out that parameter. You don't have to give error threshold and iterations. You can just give an error threshold and it will do fine. Okay, so now I'm going to call my train function. And what this train function is going to do is that it's going to go grab my data and do pre-processing of that data. Okay, so here is my data, right? So as you can see, I have name, miles per gallon, cylinders, displacement, all that other stuff. Your data is going to look like that. So you're going to have some kind of a function that is going to remove all the fields that you don't want and keep the fields that you want. In this case, I only want miles per gallon and horsepower, because that's what I'm trying to see. Is there a correlation between those 2 numbers, right? So I also define a preprocessor. That's what is going to do the step that we talked about making the data, modifying the data if we need to modify it, You can see right here the normalization of miles per gallon, normalization of horsepower, normalization of miles per gallon right there. The important thing right here is that every network, remember, every network is going to have an input and an output. So right here, I'm going to have the horsepower is my input, and the miles per gallon is my output, right? So I'm defining in there what my input and my output is going to be from my raw data. So this is saying just grab the normalized horsepower and the normalized miles per gallon from the raw data that I have. And that's going to become my training data. Okay? So once I give that information and I have configured my neural network, I can now train. So it's going to use this function to train my neural network. Now this function will give you back a JSON object, okay? Because brain stores the data, the neural network, in a JSON structure, all right? So I'm going to show you what that JSON structure looks like. And here is what a neural network output is, okay? It's just a JSON structure. It's saying that you have a neural network with one input layer, one output layer, and a hidden layer with 2 neurons, okay? And then here is the numbers that we're talking about. Here is the biases, and here is the weights, and you can see that I have 2 neurons, okay? So it's a simple equation with 2 neurons. The bias, the weight, for each one of them right there. Then we have our output layer, okay? So when backpropagation is done, it's going to grab the information that it generated from the hidden layers, put it through the output layer, and compare what the output layer produces versus what the expected output is. Okay? So that's what we have defined there. And then my hyperparameters right here. Okay? Activation sigmoid, iterations, error threshold, etc., etc., etc. So you can look at those other hyperparameters there. So that's simply what a neural network is. Now here is where it becomes interesting, right? Because you could grab that output of a neural network and you can put it on a web page. And now you have a neural network working with your website, right? That has already been trained. So this is a trained neural network. Okay? So in order to visualize this, all that I'm doing now is that I'm going to be plotting this information. Okay? And I'm going to show 2 plots. I'm going to show a plot with the raw data, and then I'm going to show a plot with the value y, the horsepower that the model returns with. Okay? The miles per gallon, I'm sorry. And then I'm going to normalize the miles per gallon because we want to see the data as miles per gallon, right? So I'm going to create a scatter plot and a line plot for you to see that. So let's see what this produces. So when you go to this, when you download this to your machine, all that you have to do is say npm start and the name of the project, the name of the example. Okay. So in this case, HP versus MPG. Okay? And as you can see right here, the blue dots represent the raw data that we had as the input. And the orange line is giving you the line that feeds that data. As you can see, this shows you right there that there is a direct correlation between your horsepower and your fuel economy. Okay?
Wait a minute. Did it analyze it, or it started guessing at what would be the rent?
No, it ran